Okay, so in this presentation, we're going to be discussing another type of committee machine, and it is boosting. In particular, we're going to focus on boosting trees, although boosting is a general strategy for strengthening a classifier. And this particular topic is talked about in, let's see, chapter 8 in the Introduction to Statistical Learning, but this particular presentation is going to follow chapter 10 in the Elements of Statistical Learning, which goes into a little bit more detail about the different methods. So let's get started. Um, I want to recap for a minute at a boost. We will get into trees and boosting trees, and we're going to talk about a method for implementing the boosting called gradient boosting. It's going to rely on an optimization approach known as steepest descent. I will introduce the gradient boosting algorithm and improvements on that algorithm by introducing a whole bunch of different things that we can do. And we'll talk a little bit about the model interpretation. So just to recap, we started talking about cart methods, and we transcended into bagging, and we started our boosting conversation with the simplest boosting method, add a boost. And this operates in a very simple way. It's reweighting the training set. So at each boosting step, it's an iterative method. Weights are applied, and you'll notice these weights go from 1 to big N. So for the training observations, there's a weight for every single one of them. So I'm writing that here is xi, yi, and I've got this going from 1 to n. So each one is getting an individual weight. Weight is updated every iteration, but without loss of generality, at the initial step, we can say that the weight is 1 over n. So at each iteration, going from 2, because I'm talking about the initial one here, to m, these weights are going to be adjusted. And those adjustments are going to be made individually. And it's going to depend on what we call the margin. So if training points are misclassified in the previous iteration, then that weight is going to be kicked up a little bit. And if training points are classified correctly, then they will see a small weight. They will still see some kind of a weight, but it will be relatively small. So there is this continuum here. We talked about different loss functions there for doing the weighting. And another weight that's going to happen is going to be the weight on the actual classifier. And this weight on the classifier is going to be a function of how good the classifier is doing, which will depend on the margin also. So the margin of all points in the training set. So this is going to carry a weight as well. And so at every step, we're kind of collecting two types of weights. This was the algorithm that I showed you. We have the initialization. We're fitting a classifier to the training data. I'm computing the error rate, which is a function here of the individual weights and the misclassifications. And I'm going to compute an alpha value here, which is going to be the weight on the classifier. And this classifier weight is a function of the error. And I'm going to update the individual weights. And this update in this setting is written as an exponential loss function. And but different things can be kind of put in here. We talked about some different functions here. And the output g of x is going to be the sign of the classifier. Because you remember that when we talked about add a boost, we talked about it with respect to a two-class problem with y is equal to minus 1 and y is equal to 1. And we did it that way because we had to kind of understand this margin idea. So the sign is enough to tell us what class that is, although typically we think about things as a dichotomous outcome with a 0, 1. Here we have to think about minus 1 and 1. Lots of different things we can do. Different things have happened since Add a Boost, and I mentioned that there's a book, a great book on boosting with all different types of methods here. So now going back to trees. We're going to talk about boosting trees in particular. So let's just formulate this problem. the tree itself, thinking about the tree itself, regression and classification trees, they partition the feature space, and they do it into disjoint regions that are represented by terminal nodes in the tree. So we've had a lot of practice at this point going between trees and feature spaces, in particular kind of drawing a tree from a feature space or drawing a feature space from a tree. We've gone back and forth, and we kind of understand how that happens. The regions are derived by this recursive partitioning, and this is used throughout in all the committee machines that we've talked about and that we will talk about. This recursive partitioning, this very simple process, is what is driving it. The prediction itself is very simple. In fact, once you identify the region, it's just a matter of sprinkling your data down the tree or mapping it onto the feature space and figuring out what region it sits into and making the prediction based on that. So here I have, if x is an element of the jth region, we have f of x equal to gamma j. So this gamma j, if it is a regression problem, it is just an average, or if it is an average of the response variables that end up in that region. If it is a classification problem, it's the majority vote. So this is, again, nothing new. We've talked about CART, but now we have to think about these things a little bit more critically. So the tree can be formally expressed as a collection, if you will, of the gamma j's and the individual regions. So here we've got a parameterization of a tree, x and theta being the parameters rj, the regions, and the values. Okay, so this is what is happening here. And if I want to make a prediction using the training set, then I'm using this formula to kind of calculate my value based on these predicted responses f of x. So this solution requires numerical optimization. How do you kind of figure out, what the appropriate trees and regions are? And in particular, the thing that we're trying to solve is a minimization, in other words, a pairing of regions and values such that you're minimizing a loss function. So that's essentially what this is saying. In this case, there are RJ regions, and we're looking over all of the regions essentially to calculate the loss of the true yi's, or your test set, or your training, whatever you're trying to figure out the error for, and the predicted responses. So that is going to solve the problem, and we've discussed that already. So the solution, in the boosting sense, is going to require two stages. And if we think about these individually, it's going to be a little bit easier. Here we have gamma j, finding gamma j. This is really trivial because I've already said in words several times, if I want to figure out what this predicted response is, or the predicted value for a particular region, I can just take the average for regression or majority vote for classification. So this is specific to regression in this example. But to actually find the regions, it's going to be a little bit more complicated. And it's even going to get more complicated when you think about finding these regions in an iterative way, because that, of course, we've talked about AdaBoost, and we know that AdaBoost is an iterative method, and so by nature of an iterative method, we are having a dependence on the iteration before. Okay? So in two dimensions, we kind of understood this visually by splitting these different half planes and enumerating all the pairs of split variables and split points, so we could actually figure that out. Okay, the boosted tree is going to look a little bit different. So here, I'm going to follow the notation in the elements of statistical learning, which is, it is consistent in the introduction to statistical learning. It's just a little bit more detail, and so you're not going to be responsible for all of these details, but I think it tells a better complete story here. So this is the prediction, kind of at the mth iteration, and here we're looking at the sum over the training set, going from m to n. M equals 1 to n of the trees, which consist of the training data and the parameter set here. This is going to be derived in what your book kind of describes as a forward stage-wise process, very similar to this forward stage-wise selection that we have done in the past, or we've discussed at least at some high level. So this is the minimization problem that is solved. So we need to figure out what the parameters are. And of course, going back a couple of slides here, the parameters define the tree. It's the region and the predictions. Okay, so the estimate of the parameters is going to minimize the loss function. And here we have yi. This is for all the training data, the loss function between yi, and this is what we're writing is a new function here that I'm writing here. And what does it mean? It means this is the functional prediction at the last iteration, and it's going to be added to the prediction derived from the new iteration. Okay, so this is m minus 1. This means, of course, there is this dependence. Okay, so here we're going to be predicting this based on can be viewed as kind of a step or a small change. Okay, so we're kind of moving in an iterative way, and every single step we have depends on the last one. And this is going to be a minimization over theta hat, and theta hat, or theta m in this case, is all of the regions and all of the assigned constants. Okay, and this is true for the next tree, and it's given the current model fm minus 1. Okay, so this is the idea. Okay, so we're going to be thinking about it in a similar way. Given the regions, finding the optimal constants in the region is very straightforward. So here I've got my theta hat, and I'm looking for the minimum of this loss function as before, but now I'm thinking about, I'm writing this more concretely. This is the prediction coming out of this particular piece of this particular tree. So it's the value assigned there. So we want to minimize this loss function. Okay. Okay, so now let's talk about how to do that. So gradient boosting is a way that uses gradients, and gradients, of course, is the first derivative of a function. So here, it's going to work with gradients, and it can work with a variety of different loss functions. The loss functions have to be differentiable, right, because we're talking about gradients. And it uses the idea of additive tree models. Now there's tons of different parameters that are going to drive this process. And I'm going to go through, and this is why I decided to use this introduction together with the elements, because the elements goes into far more detail into some of the different bells and whistles that can be added to gradient boosting. Tree size is the parameter that obviously has to be selected, and this is something that we didn't discuss, but tree sizes, because of the hierarchical nature, can be thought about as, in some ways, an order of interaction. So if you have kind of a two-level tree, that second tier can be thought of as an interaction between that feature that is used for the binary question in the second layer. And of course, it's conditional on the first layer. So this conditioning piece can be thought of in some ways as an interaction. So gradient boosting, so tree size is something that has to be set, okay? And typically it's set to be constant throughout the entire boosting iteration. And it's not going to have the same flavor as we did with classification and regression trees, where we grow things out and prune them back. That's not something we're going to do here. We're just going to fix the size, and we'll talk about some of the issues with that as well. So gradient boosting inherits all the good features of trees. Okay, it does feature selection. Okay, so it's adding in features that, it's not going to necessarily include all of the variables in your data set. It's going to take some and leave out others. It can handle missing data. So still, we have that clever way of working with surrogate surrogate variables, doing surrogate splits, we're still good there. And we can also still handle mixed predictors. Of course, it's known by the nature of boosting and by the nature of, we already know these types of penalties. It's known to improve weak features and also predictive performance. So the class of methods that we're going to be needing for this gradient boosting method rely on gradients, obviously. So you might recall the basic construction of these iterative methods relies, they're all kind of deviations of this Newton's method. And this is just a picture from a Calc 1 book. If you don't remember the details of this is okay, but you kind of think about taking an initial guess to where the zero crossing is going to be. And here, so for example, it's x1, and then you're going to ride the derivative, which is the tangent line, until it intersects a zero again. And here you're getting a little bit closer, and then you would ride this tangent line until eventually you're finding a zero, if one exists. Now, another approach is to think about using secants instead of tangent lines, and this kind of underlines the basis of these quasi-Newton methods. And they rely on f of x only to approximate the solution. And so in other words, you don't need f prime of x to be given explicitly. You can just approximate it by using what we call finite differences. And so this is just a schematic of what this might look like. It's another picture. It's just a little bit more involved than the one before it, but you might recall this from your previous days and experience. So what we have here, if we again started at an initial guess, we find it, follow it to the function, and we follow the secant line until we intersect the function again, and that's going to be our x1. Then we're going to follow the secant line again until we intersect the function again, which is our x2 here. And then finally, we're going to follow the secant line there, which is this third secant line here. It's the green. It's very close to the function until we get our x3. And then we would keep doing this, and we're kind of getting from the left and the right, getting to that zero. Eventually, we're going to converge in on that zero. So that is the idea here. And of course, this is a premise of relying on the functional approximation at these two different points. So these two different points of intersection with the secant line. So that is what the quasi-Newton method is about. It doesn't take any explicit requirement of the Hessian. This is approximated by gradients in this case. So that's exactly what this quasi means. So if you have Newton's method, you need to explicitly compute the first and second derivatives. But here we're just going to use this method of finite differences. So if we think about a general loss function, we can write it in the following way. This is the same that we've been doing before. So we have the loss, and here we have the training data and the approximation, or the y hat, which is f of xi, which is computed for each training sample, and this is going to be summed over all of the training set. And what we're aiming to do is minimize the loss of this is the function here with respect to f of x. Now in this case, f of x is going to have a very special form. So this is no different than we saw before, but now the form is going to be different. It has to be the sum of trees. And so what is the sum of trees? That is a complicated concept, so we're going to kind of get into that now. And we're going to frame it with respect to this quasi-Newton method. Okay, so this is a little bit of notation. And again, we're going to think about the approximating function, which is our y hat, at each of the data points xi. And this is going to be a collection, right, of the individual predictions for f of x1 all the way to f of xn. So this is the training set. This is what we want. We want the prediction, the full vector prediction of the training data. Okay, so the numerical optimization problem looks like this. You have your f hat, and now again, this is what we've said in words. We're minimizing the loss function, where f is this vector here. The parameters, f hat, it's a vector. It's real numbers by n. So the solution, it turns out, can be expressed as a component-wise sum. Now this is something we have to think a little bit about here. So I'm going to write fm, okay, and fm is going to be the sum from 0 to big M of hm, and hm is also a vector in this case. So, so what does this mean? Well, just like in Newton's method, we have this initial guess. So that's our f of 0. This is our initial guess is h0. That's the initial function. And we're going to update our guesses just like we saw in the Newton's method, where we're kind of updating, and every crossing of that 0 depended on where we were on the function before that. So that was an iterative method. So here's the same thing. We're going to update this initial guess at each successive iteration, and it's going to be based on the current parameter vector f of m minus 1. So this is, this is the summation, and it's going to go across all of the iterations. Okay, so we're actually expressing it as a sum of components. Okay, so h of 0 representing the initial guess, then we have h of 1, h of 2, until we stop iterating. Okay, just like the boosting idea. Okay, so the question is, how do we kind of come up with these updates? Okay, so the spoiler alert is, Newton's method thinks in the sense of finding the minimum by looking in directions of descent, right? So we want directions where the loss function is going to be decreased. And so that is, what the idea is behind the steepest descent method, which is actually general to optimization. It's nothing specific with boosting trees, but this is one approach to finding the minimum in this Newton type methods. So the steepest descent is just like it sounds. It uses an iterative method, okay, and we're thinking about approximating the function repeatedly until we converge to a minimum, and these updates are called steps, so this is a general thing. It's going to move in the direction of the steepest descent, which is in the direction of the gradient, the negated gradient. Okay, so that's what we're doing. There's a lot of questions here, when you get to steepest descent. And sometimes it can be too ambitious to step in such a direction, so we try to kind of find a compromise here. But lots of questions come up that are not necessarily unique to steepest descent, but we want to think about how long should we step, how many steps should we take. This is a stopping criteria, and this is absolutely not trivial. What direction do we step in? This is also not a trivial question. Do we want to step in the direction of steepest descent, or do we want to take some other type of direction, which is also of descent, but maybe not as steep? Steepest descent steps as far as possible in the steepest direction. Okay, so we'll kind of get to why that might not be a good idea, or at least I'll mention some reasons why. Okay, maybe you don't have a lot of trust in your model, and you don't feel like, at least at the beginning, you want to step so steeply. You might want to take some little steps, and then when you get a little bit more confident being described as some measure you're taking as you start to iterate, you're tracking some things, then you might decide to step a little bit bigger and bigger. This is reflecting the trust you have in your model. So there's lots of things you can do to modify this. These are called trust regions, and this is something specific to optimization. The negated gradient is the steepest downhill direction, so that kind of mimics what I'm saying here. So that's a pretty severe type of method, which is fine. But the direction, it takes a step, which is, I'm going to write it as minus rho m gm, and this is consistent with the notation in your book. Rho m is a scalar, and gm is the gradient of the loss function evaluated at the iteration before. Okay, so you're evaluating the gradient at the iteration before. That's what we would expect to do, right? Because our next step depends on what happens at the iteration before. Okay, so that, even though this notation may be a little confusing from that point of view, because I've got an hm here, I've got a rho m. I'm saying rho m is a scalar, gm is the gradient, okay? And it's a gradient of the loss function evaluated at the iteration before. So this is actually dependent on the iteration before, but it's written in such a way, again being consistent with your book, that this notation grabs an m instead of an m minus 1, but it's implicit because g of m is f of m minus 1. Okay, so that's where that comes in. Rho is a scalar, and this is tuned, if we just take steepest descent, it can be a 1. You could even take a value greater than 1 if you have a ton of trust in your model. The trust region approaches that I mentioned briefly in the slide before, they kind of take a row of m which is somehow tuned, and it may change. You can think of it as a learning rate almost. It may change throughout the iterations. Okay, so it can be fixed or it can change, but it's always a scalar. The gradients are just the partial derivatives of the loss function, okay, evaluated at the function before, at the iteration before. So this is important, of course, because we know what a gradient is. We know it's the derivative, but this tells us something about our loss functions. They had better be differentiable, okay, or we need some kind of way to approximate these derivatives in places where they might not be. So that's, something that is important. And the step length, rho m, is the solution to, here's the minimum here, and now this is one way to think about it, but we have a scalar which minimizes the loss here between these two, the iteration before and what's happening now. So we want to kind of stay close, so we want to find a loss that will minimize these two values. This is one way to do it. Of course, it doesn't have to be done in this. Like I said, it's a constant, and this is what your book is saying, but in the general sense, it does not have to be selected in this way. But the gradient is certainly going to be standard as it's defined in this way. So the update is the next iteration, the y hats, which they call f of m here, is the current ones, and then we have this step. Okay, this is the adjustment. This is what's going to bring it, so we might change it a little bit. And eventually we're going to keep going and changing these, and eventually we're going to see that this piece is going to get smaller and smaller and smaller as we start to converge in on our solution. And that's one of the things that we can use to decide when we're going to stop the process. Because if we are converging, we're going to see this converge to a particular value, but also these are going to be, in terms of taking, if I were to take the norm of this vector here, it would be getting smaller and smaller. Okay? All right. Now, gradient boosting does not use the straight up steepest descent, but it uses a flavor of the steepest descent. Now, there's a little bit of a trick here, and it's a kind of a difficult thing to think about, which is why the introduction book doesn't tackle it, but I want to expose this concept to you here. Now, if we were going to think about minimizing loss, if we really wanted to minimize that functional, the steepest descent would work fine, okay? But there's an important piece here, and it has to do with overfitting. The gradient is only defined at the training points xi. Therefore, this approach may not be accurate to new data. So what do I mean by that? The same thing I meant in the other methods when we talked about generalization error. We might overfit our data if we think about fitting these loss functions and using steepest descent in connection with these loss functions that depend on this gradient. So it could lead to overfitting. And so if the ultimate goal is to generalize the method, generalize the model to new data, then we have to think a little bit more clever about how to do this. And so this is a very interesting idea, this gradient boosting. So it's going to take a flavor of this, and it's going to work in the direction of this, but it's going to do it in a way that we hope will not overfit the model. So the resolution is to induce a tree, which we call t of xi theta m, as close as possible to the negative gradient. Okay, so here we are, and we're going to find a tree. Okay, so we're still going to compute gradients as we would before. We're going to find a tree which is defined. Of course, this is the training data. This is our theta m. This is the parameters for the tree. And we know theta m depends on the regions and the splits. Okay, but here I'm just bulking it up into one parameter. The theta m that we're going to pick is going to minimize the distance between the gradient and the tree itself. So it's going to be really, really close to the gradient, but it's not going to be the gradient exactly. It's not going to use the loss function explicitly, but it's going to try to get really, really close. Okay. So the point is that the resulting regions will not be the same, but they will be close. Okay, so this is a form, if you will, of regularization because we're solving, if you will, a nearby problem. Okay, we're not solving the exact problem of steepest descent, but we're trying to get as close as we can to that direction. And the corresponding predictions are going to minimize the loss function that we had before. So here, once we have the tree, once we have the parameters, of course, the predictions are going to be those that minimize the difference between the training data, the response values, and the new values, the predictions. And so we know how to take that. Once we have the regions, we define it explicitly as before. It would be a majority vote or an average or something like that. And so some common loss functions that are used for gradient boosting for regression, we have our standard residual sum of squares, and we can easily take the derivative, there. Here we have, if we have absolute loss, then we can also think about what a derivative would look like. The Huber loss, we talked about that, which was something that was kind of a compromise between these two things, but it constrained against those outlying points. And for classification, there's less available anyways in the implementations that we'll use. Okay, so this is what the gradient boosting algorithm looks like, and it follows exactly the idea that we've already conveyed, but we have some kind of an initial guess, f naught of x. Then we're going to march through 1 to big M. This is going to be decided by U. And we're going to go through, and for each of the training samples, so this is going to turn out to be a vector. Okay, so for each training sample, we're going to evaluate it at the negative gradient. So that should be defined. That's going to be defined within the package. You're going to have to select a loss function. It's going to know what the gradient is for that loss function. And here we're going to do this of course, the iteration before, using the values of that function before. So when m is equal to 1, that's going to be the initial piece. Okay, so we're going to denote this. So this is changing at every iteration m, and it's a vector, which is n by 1. Okay, so this is going to be this r. And we're going to actually, in the implementation, remember, we want to get as close as we can to this negative gradient. And so the way to do that is to fit a regression tree and use these r's as the target. Okay, so in other words, we're going to try to predict as close as we can. We're going to get as close as we can to these. Sometimes they're called residuals in this case, but they're not really residuals. It's just the evaluation of the gradient at those training points. But if we use them, if we play the game where we're going to let this be the target, we're going to find a tree, we're going to fit a regression tree. This one is going to be the target. That tree is going to be as close as we can get to this gradient. Okay? And so that's going to give us our terminal regions. Okay? Then we're going to compute the prediction in those terminal regions, which is what this is saying. This is this gamma jm. So these are going to be the predictions, which minimize the difference between the true yi's, and now we have this induced prediction here. And so this here is nothing more than we have the regions, now assign the values to the regions. So in the case of regression, which we're going to be using this for, this is going to be just the average within those regions. Okay. Then we're going to update f of m according to the last one, plus these changes that we've just calculated here. And eventually we're going to output this as the overall predictions. So there are a lot of things that we have to consider in terms of tuning. This is one of the more challenging methods that we'll discuss. We're going to talk about neural networks and support vector machines coming up here. Those are other two methods that are difficult to tune. The issue with this method and some of the other ones is that there's more than one thing to tune. So when we talked about lasso or subset selection, there was one complexity parameter. Well, tuning several complexity parameters at the same time is a major challenge. It's not really well understood what the best approach to doing that is. So to get started, one thing that we have to think about is how big should we grow the tree? So here are the values that we're trying to induce the tree to fit. And so we're going to do this at each iteration. So we're going to essentially be building 1 to m different trees. And so we could think about doing this on a tree by tree basis, kind of trying to figure out some decision rule to grow and prune every single tree. It turns out that this does not work well in practice. So this has been something that has been attempted, and it can be attempted. It's obviously not as simple as the alternative strategy, which is generally taken, and that is to take a single cutoff for the tree. So you expect the tree to have no more than so many terminal nodes, or exactly so many terminal nodes. So this J is a metaparameter that has to be decided. And so the question is, what is the effect of different size J's? So if we have smaller or richer trees, which J is kind of controlling here, what is the effect? Well, we understand what the tree is and what it means in terms of the different layers. It's a hierarchical relationship between these different values. And I mentioned in a previous lecture that the number of levels is a reflection of the number of interactions that might be expected, right? So if we, for example, split on age on the first layer, and then we split on race on the second layer, well, there's a relationship here, right? We've got age and race, and so that can actually be determined as a hierarchical relationship, but also as an interaction. So we can think of it in that way. And so one way to decide how many layers that we might have is if we have some a priori understanding of how many interactions we might expect. It's really hard to have that information beforehand. Very, very difficult to have that information beforehand. So this is not a great rule, but if you do have it, that's something that you can use. Another way to think about it is using this is saying the same thing. This is the rule of thumb. Here we have J is equal to 2 is generally too small. More than 10 is too big. Before 4 and 10 is good. So this is something, again, these rule of thumbs are kind of arbitrary too. So it is a challenge. This is just to give an impression here of, this is taken from the Elements of Statistical Learning, and they just kind of show in terms of the error when you're boosting with trees of different sizes. Okay, so here we have stumps, which is the simplest tree. J is equal to 2. Here we have a 10 node tree. Here we have a 100 node tree. And here we have add a boost, which was the first burst boosting method that we talked about. So the colors here aren't exactly easy to see, but what we see in this model, stumps, the simpler models, perform the best. That actually goes with our intuition, right? We're always looking for parsimony. So we might expect that the most parsimonious model, although they might be very crude, may actually perform the best. And then we have 10 nodes performing slightly better than that, and we have gold is 100 nodes, which is worse. It might fit the generalization error much worse. And then we have add a boost, which does not in general do as good as gradient boosting. Now, so why does this work in this case? Well, even though this is the crudest model, it's still additive in its nature. So we're taking a bunch of crude models, but don't forget we're still adding them on. It's not like we're taking them at their face value and kind of bagging them. Okay, we're actually, this is an iterative method, and we're moving in a direction toward a minimum. So this is good. It's still not as good. There's enough difference here. Remember, when we were selecting the parameters for random forest, it was very simple to see that there was really little to no sensitivity to the number of features we considered at each split. So that was another, in terms of promising and comparing these two, that's one of the benefits of random forest. So we do have to pick this. We see there's going to be a difference between these. Another thing you might think about is, how many trees should we include? So that comes down to figuring out where to halt this thing. Okay, and We can get into issues of overfitting. We just include too many trees in our model. Okay, we're not going to necessarily, like in random forests where more is more, that's not the case here. So the strategy here is to use a validation set or a test set as we would before and track that, okay? And find the M star in this case that minimizes the predicted risk. So here they use in the discussion of boosting, they again change this terminology. Risk is just meaning loss, of course, in this case. So one thing that we can do with respect to shrinkage is all of this is the same, the meat is the same, and now what they're going to do is they're going to take a term, V, and they're going to pin it on the summation here. Okay, so this is going to control the step, if you will, that is taken based on this iteration. So maybe if I make this really big, I'm going to be moving from that. I have a guess. I'm going to move far from that guess if I take this to be large, and I'm going to move slow from that guess if I take it to be really small. So this functions like a regularization parameter. You're regularizing the solution, and it's done. It can also be thought of as a shrinkage term, not in the classical sense that we've thought about shrinkage. Okay, but this is again the terminology that they use in boosting, which was really born out of an engineering kind of not group, but area. So what are we going to do here? Well, this can actually be thought of in terms of shrinkage, they call it, but it's really just a learning rate. Okay, so this is the same formula I showed before. It's another complexity parameter. It can be thought of as a learning rate. So you might otherwise take this to be small at the beginning and make it larger as you start to kind of trust your model. So that can be controlled at the get-go before entering the loop. You can range this or you can take it to be fixed. It's not surprising that there's an inverse relationship between V, this learning rate that you're taking on, and M. So if you take it to be very, very small, you're probably going to have to go through a bunch more iterations, right? If you take it to be large, you're going to be stepping in bigger ways, but you may not capture what you need in your model. So, but you won't need as many iterations. So that being said, it's a tuning parameter. It has to be selected, or a range of it has to be selected. Empirically, it's been shown that smaller values of V favor better test error. In other words, take smaller steps, don't try to learn very fast. But they require, of course, larger values of M, which is exactly what you would think. Okay. There's another possibility, yet another parameter. It's called eta, which are book covers and I'm not going to talk about it here. I don't really think there's a ton of value to this particular piece, but you should read it. So if you can think of how you might further improve this particular method, one approach is to think about subsampling. Subsampling is something that is done it's very intuitive. I haven't covered such techniques, but you can imagine if you've got your training data, you kind of take a subsample of this data. So it's a subsample would be of size M, which is less than N, and you would fit your model on those different subsamples. So in a way, it's like bagging, but it doesn't have this property. It doesn't absolutely ensure that the training samples are going to all lie within, be represented in a favorable way throughout these different subsamples. So this is a topic I try to avoid, but it's something that can be controlled also within this. I don't believe it's included in the package either. So this is two different types of trees, and with and without shrinkage. Now this is for classification. So they're using deviance here and misclassification rate. And these are two different levels of trees going this way. So here I have stumps. So that's very simple tree to a 6-node tree, which is also. So let's just kind of look at the stumps first. So the red is no shrinkage. So what we see, these are the boosting iterations. This is test error. So we're kind of going down with shrinkage, and we go down and look at this. We're actually learning, we get down faster, and then we start to go up like this, okay? Where this shrinkage piece here, this is with no shrinkage, the blue is the shrinkage, and it also goes down, in the same. It doesn't go down quite as fast, okay, because we're shrinking the learning rate, so it's going to go down a little bit slower, but it's going to do a little bit of a better job in the end of finding that good model. Okay, so this is 2,000 iterations. Now it's not going to come back up at this point, although we would expect eventually it would. The misclassification rate, we have the same thing. We have no shrinkage. It dives down a little bit faster, like we would expect. The shrinkage one at 0.2, right? Because in addition to deciding that you're going to use shrinkage, you've got to decide what that value is going to be. So it's a slower learning rate. We're cutting the learning rate by about 80% in this case, right? This is going to go down a little bit softer, but it's going to find a solution that's slightly better. And the same is true here. Now for deviance, it turns out in this case, this is a 6-node tree. It's going to become more important when you have trees that are a little bit more complex. Okay, so then you really want to put the brakes on the learning rate. Okay, so that's something that you will also kind of learn empirically that is the case. Although this is not stated as such in your text, we can see that it's true in this particular case. Deviance is also a little bit more sensitive. So here we've got shrinkage of 0.5. So we're kind of, it's really stabilizing things. It's slowing that learning rate down. With no shrinkage, this thing just launches off. Okay, so this would be the minimum, if you will, for no shrinkage. But here we can see that we can do much better than that, even though it takes us a little bit longer. Okay, so again, we have that inverse relationship between the shrinkage and the number of iterations m. Finally, for misclassification in the 6-node tree, we see something very similar to what we saw over here. Okay, so there's a couple other things to take home here. Deviance in particular is a little more sensitive. If you're going to use deviance as the loss function, you should probably apply some kind of shrinkage. And the level of shrinkage, you know, these are two different levels of shrinkage, but I think this, of course, is more conservative. This is not, but they both are kind of achieving the same thing in this example. I don't think it's obvious how to take that level of shrinkage, but you can think of it as, if you think of it as a learning rate, you can apply it in that sense. The misclassification rate in general is not as sensitive, even with richer trees, the 6-node tree, to this type of erratic behavior. And in this particular case, the shrinkage does not appear to benefit as much as it would with the deviance. Okay. Then we have the number of trees. This is something else that we talked about. I mentioned this already. This has to do with the subsampling, so I'm going to kind of choose not to go into a lot of details here, but this, if you so decide to use this, it's also called stochastic gradient boosting. It's subsampling of the data. You get less computation. There's lots of benefits, but you end up, of course, if you keep doing all of these things, we have to decide the number of how complex the tree is going to be that is fit to this. How complex is this tree going to be? Is it going to be a stump? Is it going to be a 6-node tree? Then we must decide m, the number of iterations we're going to use, what the learning rate or the shrinkage parameter is going to be. And now if you add this piece, now we have to think about subsampling on top of that. Okay? And so, your book, The Elements of Statistical Learning, goes into, comparing these different flavors and no shrinkage. Here's deviance again. This is absolute error. This is a 4-node tree. But they also show in this particular case this gray line, which is subsampling, which I just want to focus on the gray and blue lines here. So we already know, that with doing nothing could be an issue, especially with deviance. Subsampling is purple, and now look at what happens with, if you just do subsampling, that's also not good. Look at this, and even in absolute error, it's not good. And so in general, I also advise against subsampling for a whole slew of other reasons. But when it's coupled, they want to show you that when you couple it, which is the gray line, when you couple it with shrinkage and compare it to shrinkage alone, it can do a little bit better. And that's shown in this particular example, but here it is not compelling. Okay, so there's a slight difference here, and then it starts to creep back up, but here it does only marginally better. Here there's quite a difference here, but we don't really understand what the behavior is going to be out in this range also. So there could be some benefit to it, but it can also be erratic. Other things you want to think about. You don't have any good interpretation anymore. You had the nice interpretation looking at a tree and understanding the variables. You had measures of variable importance. Those are lost. So if you want to think about interpretation, you need to think about other ways to do that. Even relative importance is more difficult in this case. This can be computed. It requires a little bit more in terms of how you're going to account for these other, we're calling them nuisance parameters, but essentially all of these things that we're doing here, right? So it can be a challenge. It can still be computed in the same way that we have seen before. So in other words, I saved this lecture for last. It's a pretty complicated method. We've talked about the negative gradient, the steepest descent, how we're going to have to be a little bit more clever in terms of how deep we want to step, but also if we're going to step in the direction of steepest descent, that we may in fact overfit our data. So inducing a tree in the steepest descent is kind of a wild idea, very clever idea. So the book talks about it in terms of being greedy and not greedy. Okay, so that I suppose is one way to think about it. So they also term it as a residual. The residual, it's not truly a residual in the classical sense, but it is the negative gradient defined of the different functions from the iterations before. This is a quasi-Newton type method. Okay. Now, so these are the details. The devil is in the details, right? But from a practical point of view, we understand that steepest gradient boosting can do better than AdaBoost. We know that. We know it can do better than even random forest, because even though we talked about the random forest paper in the textbook, you will see, if you look in the random forest chapter, you'll see many examples which say that gradient boosting is still better. Okay, so we know it can be good. It's not always going to be better, but we know it's worth a shot, and we know that we can make improvements, which are not easy to define. For example, how many iterations, how big your tree is, if you decide to use some subsampling, how many subsamples you're going to use in your set, and also shrinkage. So these things are very difficult to set altogether, but if you can do it well, it will work. Okay, so that's where I want to leave it, and now you have the background that you need to go to the computer and start to look at these different ideas using the GBM package in R, or if you so choose to use Python, that will work as well.